Chapter 10, we're going to be looking at hypothesis testing. Now, this is one of the most important concepts in inferential statistics, and it's probably the most difficult also. We're not going to be spending much time on the math, and the math part of this really isn't that important. What is important is that we learn the logic behind hypothesis testing so we can actually tell what's going on when we say something like, oh, p is less than 0.05, the results are significant. So that's what this chapter is trying to do, is trying to help us to understand what a significant result is when we look at some data. Now, I want to start off with a question. And you might be familiar with my friend Beep Beep, and he's a bear who likes cookies. Yeah, I know. And he claims to have cookie power. When he eats cookies, he believes that he can get coins to land on the same side, heads or tails. For example, he's got some coins in his hands now, and he is going to shake them up. I'm shaking them. And he's going to let them land. And there were 10 coins, and he got 7 heads. Cookie power! He got 7 heads out of 10 coin flips. Is that an indication that he has cookie power, that eating cookies enables him to get all the coins to line up in the same direction? Well, you might be skeptical. You might say, well, you could have gotten that by chance. Or you might be saying, oh yeah, well, he got 7 out of 10. That's not bad. Well, that's what we want to be able to answer in hypothesis testing. Are the results something that you could reasonably expect by chance? Or are the results so different that from what you'd expect from chance that you'd say, oh, well, I guess he probably does have cookie power. So that's what we mean by hypothesis testing, to see if we can test out some statement like Beep Beep has cookie power by looking at the data and seeing if we could get that data if the hypothesis is not true. Now, what we're going to use in this example, and what Pagano's textbook uses, is we're going to look at the drug Marinol. Marinol is a pill containing THC extracted from marijuana, and it's used to increase appetite in AIDS patients and decreases nausea in cancer patients. So it's kind of like all the benefits that people claim from medical marijuana, except doesn't make people want to sit down doing nothing. It's not addictive, doesn't cause lung cancer. There's no indication that it causes schizophrenia. It's not associated with bipolar disorder like marijuana is. We don't have the as much data on as we want, but there's a chance that it's not nearly as dangerous as marijuana is, especially in terms of loss of intelligence and schizophrenia. Now, you might notice I'm kind of biased against marijuana use. I am very biased against marijuana use. It's kind of wreaked horrible damage in my family. I had a cousin who was killed trying to steal marijuana from a farm, trying to harvest it before the owners of the farm tried to harvest it. He wasn't the brightest one in the family. Had a couple other cousins that have struggled with homelessness all of their life because of marijuana use. Had another relative who just became absolutely useless in life. I haven't seen very many positive things happening from marijuana use. So I am very biased against marijuana use, and I will admit it in this in here. But we're going to look at how THC, a study that we could design with Marinol, a THC extract, or THC extracted from marijuana. Now, in this Marinol study, there are 10 people. So we're going to say n equals 10. And it's they're placed in 2 conditions. The experimental condition is they're going to eat Marinol before a meal, and the control condition is they're going to get a placebo, a fake pill, before a meal. and 2 scores are going to be recorded for each person. On day 1, they're going to eat food with Marinol and measure the number of calories. And day 2, they're going to eat food eaten with the placebo. And the hypothesis is that Marinol affects appetite. That on the average, what they're going to eat is different with Marinol than without Marinol. So here we have the results. In each line is a patient, and each column is a variable. So we've got the patient number, we've gotten the number of pills that they ate with the THC pill, the experimental condition, and then here we've got what they ate without the THC pill, they got the placebo pill, and here's the difference. If they ate more with Marinol, they got to have a positive score, and if they ate more with a placebo, they got a negative score. So this is an experiment. We're looking at 2 variables. The independent variable is whether THC was consumed before the meal or not, and the dependent variable is how much they ate. We measured that under both conditions, and then we calculated the difference. And so as we can tell, most people ate more with the Marinol. In fact, 9 out of 10 did, but there was 1 that didn't. And now, is this one that didn't? Is that sufficient evidence to say that, oh, Marinol doesn't increase appetite? Or would we say that, oh no, we couldn't get these results by chance if Marinol didn't do anything? This would be just too freaky to get 9 pluses and 0 minuses. So that's what we want to examine. Can we come to the conclusion that Marinol affects appetite given this data? Now what we're going to do is we're going to use a sign test. And this is a real simple test, and it's useful because it makes everything to a binomial distribution where we can calculate the probabilities real easily. We're not going to really, using the sign test in real life isn't done very often. And so what we're going to do is we're only going to consider the results, the sign of the results of the test. Did food consumption go up or down? And for 9 out of 10 people, the food consumption went up, so we're going to say there were 9 pluses. That other person's a minus. There was 1 minus. Now, our conclusion is, does this mean anything? Or could this just happen by chance, this 9 pluses and 1 minus? Now, the way that we're going to answer it is we're going to look at the probability of getting these results by chance. If the probability of getting 9 out of 10 scores to go up by chance alone is 1 chance in a million, then these results are important because that probably didn't happen. However, if the probability is, say, 1 in 3, then these results might not mean much. Oh, yeah, we could have gotten that just, there's 1 in 3 chance that we would get something like this. So what we want to do is we want to see how unusual these results are to see if we can come to the conclusion that, oh, it doesn't look like it happened by chance. Now, what we're going to do is we're going to look at several key concepts in hypothesis testing. We're going to look at the alternative hypothesis, and that's what we want to look at. We're going to look at the null hypothesis, which is the opposite of what we want to test to see if it's true. The alpha level, which is kind of like our criteria for whether something is worth writing home about or not. We're going to look at the number of tails, whether we have a directional or non-directional hypotheses, and we're going to look at type 1 and type 2 errors. Let's talk about our H1, this is the notation for it, and it's called the alternative hypothesis. And this is what we suspect is true. Now, this is kind of a funny name for it, the alternative hypothesis. If I were creating statistics, I would call it the main hypothesis. But for historical reasons, it's become the alternative hypothesis because it's the alternative to what we'll see as the null hypothesis. So H1 is a hypothesis that claims that the difference in the results between 2 conditions is due to those conditions. So we're saying that Marinol affects appetite. That means people who take Marinol will eat different amounts than people who do not take Marinol. And it's because they're taking the Marinol that they're eating the different, they're eating different amounts. So it's got to be, our hypothesis is saying that the change in appetite is due to the Marinol. It's not due to something else. Now, this alternate hypothesis, our main hypothesis, can be directional or non-directional. Non-directional just says that there's going to be a change. Marinol affects appetite. It can increase appetite or it can decrease appetite. A directional hypothesis, what we're going to call a one-tail hypothesis, says, oh, it's just going to go off in one direction. Perhaps Marinol increases appetite. That means people who take Marinol will eat more than people who don't take Marinol. Or it could be a one-tailed hypothesis in the other direction. Marinol decreases appetite, and people who take Marinol will eat less than people who do not take Marinol. So we can have either type of hypothesis, non-directional two tails or directional one tail. Now, the null hypothesis is the exact opposite of the main hypothesis. The null hypothesis says that any difference between the two groups is due only to chance. So if there's a difference in how much people ate, it wasn't due to the Marinol, it was due to chance. Now, the null hypothesis and the main hypothesis are formulated in such a way such that the null hypothesis is the exact opposite of the main hypothesis. If the main hypothesis is false, then or if the null hypothesis is false, then the main hypothesis must be true. For example, our main hypothesis is Marinol affects appetite. Our null hypothesis is Marinol does not affect appetite. So that means one or the other has to be true. This Marinol does not affect appetite, our null hypothesis, that means that people who take Marinol eat the same amount as those who don't take Marinol, and that any difference between them is just due to chance. It's not due to the Marinol they've taken. So we can say that the alternate hypothesis and the null hypothesis have to be exclusive and exhaustive. Exclusive means they can't both be true. Exhaustive means they cover all possibilities and one has to be true, which means one and only one has to be true. Either Marinol increases appetite or Marinol does not increase appetite. Now let's look at let's continue looking at the null hypothesis. So the null hypothesis needs to be formulated in such a way to include the possibility that the only reason for difference is chance. So if that's true, we can calculate the probability of getting the results we have by chance, because we've seen that we can calculate the probability of getting different things, such as binomial distribution or normally distributed continuous variables. We'll be able to calculate that probability of getting something by chance and judge if we should retain or reject it. Now, this is a really weird concept. We don't ever think like this. We'll look at the results, say, ooh, could we have gotten these by chance? And if we say, no, it's too freaky, we're going to say, no, we couldn't have gotten by chance. Therefore, the null hypothesis is false. It's to be rejected, which means the alternate hypothesis is likely to be true. So our null hypothesis here is Marinol does not affect appetite. And if we conclude that it's very, very unlikely that we got our results, our 9 pluses by chance, we can reject the null hypothesis. And so if the null hypothesis is false, then the alternate hypothesis must be true, because they're formulated to be exactly the opposite. Now, at what point do we decide to reject the null hypothesis? At what point do we say, ooh, this is too freaky, it couldn't happen by chance? Or at what point do we say, oh, this is really interesting, I should write home about this? We need to come up with some type of decision rule for rejecting the null hypothesis. And if we do reject the null hypothesis, we're going to use the term significant to define the results, or to describe the results. Now, this cutoff point that we choose is called alpha. And usually in science, we chose alpha equals 0.05. And that means if there's less than a 5% chance of getting our results simply by chance that Marinol didn't have anything to do something, we reject the null hypothesis and conclude that our main hypothesis probably is true and that Marinol affects appetite. Now, in the Marinol experiment, we got 9 out of 10 pluses. What's the chance that that happened randomly? That's going to be our p-value, or the p-obtained value. We want to find out what's the chance of getting these results randomly. So we're going to call this a little p. Our null hypothesis is that Marinol does not affect appetite. And so if the probability of getting 9 out of 10 pluses by chance is less than 0.05, we can reject the null hypothesis and conclude that our main hypothesis is true. Now, to calculate this probability, we're going to use the binomial distribution to test the null hypothesis. So we have 10 patients, so that's 10 trials. P is the probability of getting a plus with any one patient by chance. That's 0.50. It's like a head flip. People are going to either eat more or less for the next meal, and if it's happening randomly, it's a 50-50 chance. Now, the number of P events that we're interested in is 9. We got 9 P events. And is it going to be cumulative? No, we're just going to look at 9 for right now. Later, we're going to do a little bit more, and we're going to look at besides now. But we go into we type this into our binomial distribution equation in Excel, and we find that P obtained, is the binomial distribution for n equals 9, or 9 P events, n equals 10, p equals 0.5, not cumulative. It's 0.0098, so we can reject the null hypothesis. This is too freaky. It didn't happen by chance. Well, actually, let's tweak this a little bit more. So in this experiment, we just calculated the probability of getting exactly 9 pluses. It's more correct to calculate the probability of getting any outcome at least that extreme, because we could have gotten 10 pluses and we would have been like, yeah, that's even stronger evidence. So our hypothesis is Marinol affects appetite. That's a non-directional appetite. Maybe Marinol makes you more hungry. Maybe it makes you less hungry. Both would be evidence of that hypothesis being true. So we should calculate the outcome for 9 pluses and 10 pluses as just extreme, but 9 pluses is just as extreme as 9 minuses, so we should calculate for 1 plus, and we should also calculate it for 0 pluses, because that's like getting 10 minuses. So we want to calculate the areas underneath the two tails to find out the probability of getting something at least that extreme. So here we've got the binomial distribution with all the different probabilities. We've got going from 0 to 10, and we can see that the ones in the middle are the most common. And we saw that there's only a 0.0098 chance of getting exactly 9 pluses. But we want to look at anything at least that extreme. So 9 and 10, and here 1 and 0. We want to find the area in the two tails there. So we want to find the probability of a 0, 1, 9, or 10 pluses. And that's going to be the probability of a 0 plus a probability of 1 plus a probability of 9 plus a probability of 10. So we can use the binomial distribution command for the 4 values, 0, 1, 9, and 10. We get 4 values, and we add them all up, and we still see that it is very low. It's only 0.0216, so it's about 2%. So we're going to reject the null hypothesis using an alpha level, using a criteria of 5%, 0.05. So we come to the conclusion that the null hypothesis that marijuana does not affect appetite is not true, and we're going to retain the hypothesis that Marinol affects appetite. Now let's talk about one or two-tailed probability evaluations. So our hypothesis was that Marinol does not affect appetite. That means that we would reject the null hypothesis if people ate more or if they ate less, if appetite went up or down. So this is a two-tailed, or called, that's a non-directional, can go in any direction, probability evaluation. And we said it had to be less than 5%. So that means the rejection region of the bell curves, there's 2.5% in one side, 2.5% in one side. And if anything fell in these points more extreme than 2.5%, we'd say, aha, that's not very likely. So we would reject the tail. But we could have said, oh, I don't care about appetite going up. No, I didn't care about appetite going down. These people are starving to death anyway. We just want to find out if it causes it to go up. We could just check to see if the appetite went up. We wouldn't care about the cases with the 0 and 1s. We would just be interested in the 9s and 10s. And so that way, we would reformulate our main hypothesis. Marinol increases appetite. That's a directional hypothesis, a one-tailed hypothesis. And so the null hypothesis would be Marinol does not increase appetite. But if we have a directional hypothesis, the tail that would allow us to reject the null hypothesis moves from 2.5% to 5%. So if we make a directional hypothesis, it's easier to be sure about our conclusion. So we should always make a directional hypothesis if we can. It's easier to reject the null hypothesis. But if we need to be concerned about both directions, or if we really don't know, then we have to make a non-directional hypothesis. Now, in the next Excel example, we are going to look at an example of a church brochure that I used when I was a pastor. Many of you know that I was a pastor for 17 years in France, and we were working on starting new churches filled with people that love the Lord, and we wanted to communicate to people that God was alive, that He spoke through the Bible, and that He was changing people's lives. And we, when we were in France, we started a couple new churches that are filled with people that discovered God and His Word. But we're continually trying to help these churches grow and reach more people. Now, it would turn out that about 25% of the time, a visitor would come to a Sunday service when there was no outreach activity. So about 1 out of every 4 times, we'd get a visitor in church, and that would be their introduction to the gospel. But we designed some brochures to get more people to come. Now, on the next slide, we've got a scan of the brochures, and now these scans aren't very good. They're not very colorful. Now, this was in the 1990s. So this is when colored printing just became reasonable price. So we did something very 1990s, and we made these incredibly bright colors. We had kind of fluorescent text with pastel backgrounds, very, very 1990s looking. That's me and my family back then in the 1990s. We were all a lot younger, especially my kids. They're adults now, and the title of this was Une belle maison, une voiture de rêve, une haute technologie, un portefeuille impressionnant, du plaisir à volonté. N'y a-t-il rien de mieux dans la vie? Which means a beautiful house, a dream car, high technology stuff, lots of money, unlimited pleasure. Isn't there anything better in life? The 1990s were a time of fast economic growth with a lot of materialism, and one of the things that the gospel does is it meets people's needs in a way that materialism and pleasure can't. And so the invitation was basically a discussion of how some people have found what they believe to be better than this materialism, and that we believe that the God of the Bible was actually still alive and still talking to people, and we invited them to come and try to discover God in the Bible with us. And so that was the brochure, and we used it a number of times. We did mass distributions about 5 times, and 4 out of 5 times, visitors came to the next service. Now the question is, Ooh, does that mean that the brochures worked? So what we can do, and what we're going to do in the next Excel uh, problem, is we're going to test this hypothesis. So the hypothesis was that more visitors come when brochures are distributed than when they don't come. And the null hypothesis is that the same number or fewer visitors come when the brochures are distributed. So what we need to do is we need to know what's the probability that visitors would come at least 4 of the 5 services following distributions if the null hypothesis is true. And if that's not very likely, then we're going to reject the null hypothesis that the brochures don't work and say, oh, it's very likely that the brochures did work. So that's what the next video is about.